Let us go ahead and demonstrate the concept of a generalized state of plane stress, and we'll do that through an example that is actually a state of plane stress. And that is a valid discussion because plane stress is a special state of generalized plane stress, with the third direction being having a normal stress of value 0, right? But in doing so, we will still be able to demonstrate some concepts that are associated with a state of generalized plane stress, plus I will have a chance to demonstrate something which I mentioned earlier. So we're going to pick a stress state at a point in the structure. Okay, we're at a point in some structure that is loaded, and at that point, the state of stress with respect to some default coordinate directions that are provided, which define these planes and hence this original picture, the state of stress is represented geometrically as all the stress components are in MPa, 40, and the other one is 20 PA. Now, I have this picture and I have some orientations of the normals to the planes, but so what shall I call these directions? I can call them x and y, and the out of plane direction would be the z direction, but I'm not going to do that. That's our default case. That's what we're going to stick to most of the time, but we don't have to. So let's pick another one. Let's call this zx, and with the right hand rule, this is going to be y. So then I have to assign the values of the stresses. There is on the plane with normal z, there is 60 MPa, and on the plane with normal x, there is 40 MPa, and there is a shear stress that's equal to tau zx. It's equal to 20 MPa. So that's the picture. Those are the values that are associated with this picture. Now remember, nothing else is indicated, and therefore sigma y, the normal stress in the third direction, it's 0, and also tau yx is equal to tau yz. We think it's 0, so it's a state of plane stress, but simultaneously generalized plane stress with a special value of the normal stress. These always have to be 0 in both cases. All right, so now I'm going to go ahead and try to draw the Mohr circle. And the Mohr circle looks like this. So that's sigma, that is tau. The first step, remember, is to pick the points correctly. Here, z is the horizontal direction, so the z point will have a sigma z minus tau zx, and the other point, x, is the vertical, it's like y in our default picture. This is the y point, sigma y plus tau zx, and so this is going to be equal to 60 minus 20, that is going to be equal to 40 plus 20. That's our default choice. So then I'm going to go ahead and put those on our map. So 60 minus 20 is going to go over here. So let's say over there. Maybe a little bit further down. And 40 plus 20, it's going to go up, say there. Okay. So this here is the z point. 60 minus 20. That one over there is the x point. I should probably correct this error that I made. It's the x direction, so this should be sigma x. I'm sorry, I'm correcting. Okay, so then I would like to draw the circle. And so this is going to be my dial. And the circle is going to be not a very good circle, but it's more like in Mohr's ellipse, not a circle, but never mind. So this is A, which is the center again. This is 50. Okay, that's easy to determine. The radius is equal to, let's calculate that very quickly. So that's 60 minus 50, so that is 100 squared. 10 squared is 100, and then there is 20 squared 400 square root 22.36. Okay, so let's take that to be 22.4 roughly. Okay, so I am rotating through a certain angle, so this would be a rotation twice the angle of rotation that takes me to the principal direction, and the angle of rotation now is with respect to the y direction. Okay, and that would take me onto a plane where the principal normal stress, so z rotates there, so I'm going to call it sigma 3, which is equal to 50 plus the radius, so 72.4, and that point is going to be the rotation of x, so that's sigma 1, and that's going to be 50 minus that, in other words 27.6. Good. So now if I were to try to depict that over here, I would have, right, the direction 3 and the direction 1, and that would be theta. Same direction, here we have twice the physical rotation. Okay. Now the third direction, now I remember, is automatically a principal direction, and in this case it's equal to 0. So there is actually a third principal stress, and it's actually exactly equal to 0. It is exactly equal to, in general, it's exactly equal to sigma y, but here it's equal to 0. So that's the third one. So now we have this alternative picture. Let me draw it over here. The principal picture is the third direction, okay, the y direction, and 3 and 1, okay? And with respect to that picture, I have sigma, just let me correct this. This is 3, this is 1, so this is supposed to be 2, okay? So sigma 2 equals 0, sigma 3 equals 72.4, sigma 1 equals the value 27.6, right? So now that I have those, I'm going to look for planes that deliver me to the plane associated with extremum value of shear stresses. Now once I have that picture, I can rotate now. I will have 3 possibilities. 1, I can still rotate about 2. In other words, I can start either from here, but I can equally start from here. As I said earlier, this is just our principal picture. And I can rotate, I remember, through an angle of 45 degrees with respect to that picture. That would be that direction, okay? So that's one direction, that's another direction. That would send me onto a plane, right? A plane that on which I would observe, that's the normal to the plane, on which I would observe a 45 degrees maximum shear stress, okay? Extremum value. This is 2 theta s with respect to the original picture, okay? So this is the absolute value, the extremum value of the shear stress. Let's call that, okay, tau with respect to 1, 3. It's about the 1, 3 or about the 2 axis, so I'm going to call it tau 2. And the value is the radius, 22.4, okay? Now, a typical question arises immediately. Well, why am I doing all of this? Remember, I'm at a certain point in a structure. There is a structure. Let me repeat that picture again and again. And the structure is loaded in some fashion. There are torques, maybe loads, and eventually bending moments. This is just a generality. I'm not saying that the state of stress comes from that. Indeed, it cannot. But nevertheless, this is what we can do in ME 231. And I'm looking at a certain point, and at that point, I have that state of stress with respect to xz, but I'm interested in whether at that point the maximum shear stress that I can find actually can exceed a certain critical value. Now I search for all rotations about the y-axis or about the 2-axis, which is the principal direction, and I see that if I go up to a point, up to this point, which is located like this for rotations about the y-axis, the shear stress I observe is 22.4, which is certainly larger than what I found earlier, right? And so this appears to be a more critical orientation than the original orientation. So this plane is less critical with respect to that plane, right? So this plane now I found out, and on that special plane there is an extremum value of the shear stress, which is this. Okay, so this is more critical than that. This plane is more critical than the original picture's plane, right? But is that the most critical one at that point? If I want to search, I need to rotate in all possible directions. So once I have this principal picture, I can rotate not only about 2, but also about 3, in other words, within the 1, 2 plane, or about 1, in other words, within the 2, 3 plane. Okay? So if I make this picture a 3D picture, so the 2 direction is out of plane, but if I make it 3D, so I have some coordinate system orientation that is like this. This is the 3 direction, this is the 1 direction, this is the 2 direction. If I rotate about the 2 direction, I'm about within the 1, 3 plane. The max shear stress I observe is tau 2, okay, which is 22.5, but I can rotate about the 1 direction or within the 2, 3 plane. I can look at possible rotations about 1, but which lie still within the 3, 2 plane. Okay, so this would be a new orientation of 2 prime or 3 prime. This is not anymore some now y prime or z prime, because I've completed the rotated first and then I'm rotating on top of that. This is an absolutely new set of directions. Okay, now I'm looking at all possible orientations about those principal directions, and that rotation is about the 1 axis or within the 3, 2 plane. This is 3, this is 2. Those rotations have to do with this Mohr circle. Okay, and there is yet another Mohr circle, which is rotations about the 3 axis or within the 1, 3 plane. You could rotate to a new set of values, 1 prime and 2 prime. I'm not drawing those to make everything not too busy, but you can rotate about within the 1, 2 plane or about the 3. So 1, 2 plane would correspond to that. Okay. So when you rotate up within the 1, 2 plane, the max shear stress you will ever observe, the third direction is the principal direction. Okay. The max direction is 1, 2, so I'll call it tau 3. It's equal to the radius of this circle. The radius is half the diameter, 27.6 divided by 2, right? So it's going to be 13.8. Okay? But if I rotate about the, so this is within the 2, 3 plane, or I rotate about the 1 principal direction, the first principal direction, then I obtain, so 2, 3, which is tau 1, about the 1 axis. So I will obtain, now the notation becomes even more clear. I'm rotating about the first principal direction. And first I need to determine what those directions are, right? Because it's a relative rotation. And that rotation is going to deliver me an extremum value of half of that, which is 36.2. Now, therefore, we obtain the critical observation that when we really consider the picture point of view that we have a generalized plane stress even with sigma y equals 0. Okay, so it's a state of plane stress. So far we had only drawn the green circle. But now we have to go ahead, and if we consider everything else, then what we observe is that actually you can find the maximum shear stress for all possible rotations at this point. And now rotations are in absolute 3D. First you rotate about 2, and then you rotate about 1. Okay, you rotate about 2, find the first direction, and then you rotate about 1. So which means that if you had your original coordinate system x, y, z nicely oriented like this, first you rotate about this, and now you rotate about, right? Rotate about this, and then you rotate also about 1. So now you reach a completely new orientation that's got nothing to do with the original set of axes. It's a complicated orientation, and on that orientation there is a plane eventually where there is a shear stress that is larger than all of the other ones. Okay. So such a stress is called the absolute maximum shear stress. So with respect to every rotation, there is an extremum or maximum value that we observe, but there is one that is the largest among those, and we call that tau max. So tau max is the maximum of all the taus, tau 1, tau 2, tau 3. In this case, it is equal to tau 1. So what we observe is therefore that despite the fact that we might have a state of plane stress, we have to always draw all the Mohr circle, all three. In other words, the Mohr circle that we are drawing as if we have a state of generalized plane stress. Also, in other words, considering the third principal stress, in this case, sigma 2 equals 0. We have to also take that into account in order to decide the maximum, absolute maximum shear stress that we can observe at a point and to identify that correctly. Okay, so this was a very nice example where we demonstrated and introduced several concepts at the same time. So I would suggest thinking about that carefully, but now I'm going to solve yet another example where we will try to go over the same type of calculations once again. So let's solve yet another example that has to do with the state of generalized plane stress, and this time I'm really going to pick an example that actually is a state of generalized plane stress, and that example is one that is associated with, if you like, our default picture. In other words, the third direction is going to be the z direction, where we observe a stress of 30 MPa, and then there's going to be a x and a y direction, and there will be shear stresses. The shear stresses are 60. All the stresses are in MPa, and then there's 100 and there's a 20 MPa for the remaining two. So my default directions are x, y, and the z direction. Okay, good. So now what I know is that I don't have to write this explicitly, but I do see that this is automatically sigma x, this is sigma y, and this is tau xy. The directions are default, and this is sigma z, and I see that it is simultaneously the principal stress sigma 3 because there is no shear stress here. So it's a state of generalized plane stress. And what I'd like to do is find the absolute maximum shear stress in this problem. Okay, so that's the question that we'd like to answer. So we go ahead and draw the Mohr circle, and for that purpose, now at this time I guess we are very proficient, but nevertheless I will go ahead and identify the points of interest to us. So there's going to be an x point, which is sigma x minus tau xy, which is therefore 100 minus 60. There is a y point, which is sigma y plus tau xy, which is 20 and plus 60. And then we will draw the Mohr circle. This is sigma, this is tau. So first we put our points on the map. We have 100 minus 60. So let's pick that point to be here. And we have a 20 plus 60. So that's 60. There's going to be another 60. And so probably over here is a good choice. So that's the x point, 100 minus 60. That is the y point, which is 20, 60. And then I can go ahead and draw the dial. And then draw the Mohr circle. Now you see that now the Mohr circle is going to move into the negative axis. Okay, like that. that is our center. A is equal to 20 plus 100 over 2, that's 60 MPa. And the radius we can easily calculate. So the radius is, say, 100 minus 60 is 40 squared, plus the shear stress 60 squared is the vertical distance, square root, which is approximately 72.1. Okay. So therefore I have the first principal stress, which is sigma 1, 60 plus that value, so in other words 132.1. And at that point I will have 60 minus that value, minus 12.1. Okay. Now therefore the so this of course is our 2 theta n. We're not calculating that explicitly, but let's go ahead and write the value of 1, and that is sigma 2. Let us go ahead and indicate this to be tau 3, which is now, it is equal to the radius, which is equal to 72.1. Okay. Okay. So now there is the third one, however, that we shouldn't forget. The third one is 30 MPa. So if that's 60, there is a third one. So that's over here, which is sigma z, which is 30. So there is one more circle over here. Okay. And so that more circle is sigma 2, 3, that's within the 2, 3 plane, and then there's going to be another one within the 1, 3 plane. So that one would be this one. Okay. And associated with this circle over here, there would be a tau, it's within the 3, 2 plane, so that would be a tau 1. So it's the radius of the circle, so it's sigma 3 minus that divided by 2 would be the radius. So it's 30 plus 12 divided by 2, so that's approximately 21. Say 2105. And then there is that one, which is going to deliver a extremum value of rotations about the 2 axes, so that's tau 2, 132 minus 30, so 102 divided by 2, so this is 51.05. Okay, and therefore the absolute maximum shear stress is 72.1, and it occurs on the plane, on a plane that is defined with respect to rotations about the 3 axis, about the z-axis. So in this case it's simple, you just rotate about the z-axis through an angle 45 degrees on top of that theta n. So you first reach the principal direction and then another 45 degrees, and that would define you a plane with the absolute maximum shear stress.